I, Amit from Aspiring Minds, welcome you to this talk by Professor Sunita Sarawagi on the subject Teaching Machines to Read and Write Our Language. Professor Sunita is the Professor of Computer Science and Engineering at IIT Bombay. Her topics of interest span several fields including machine learning, data analytics, databases, and statistics. Her current research interests are sequence model for text and time series, domain adaptation, effective human intervention in learning, graphical models, and structured learning. I would request her to come on stage and lead the talk. Thank you.
I'm already on the stage. Most of you, when you were first introduced, are you able to hear me well? Okay. So most of you, when you're first introduced to a computer, in parallel, you must have learned a language with which you instruct the computer to do whatever you want the computer to do, be it make some calculations or process some data or to draw a picture. So those languages could be something like Python or C++ or Java. And these languages, if you have ever struggled with them, have a very strict syntax. And if you compare that to the richness and variety that natural languages like English and Marathi offer, you might think of computers as being really backwards. But now in this talk, we are going to demonstrate various ways in which now even modern machines can understand human language. And we are going to ponder on how computers achieve that feat. Today, even a child can get a computer to play music or find near restaurants near them or get a computer to tell a joke by talking to their home devices like Alexa or Google Home in a natural language. So suppose for lunch, if you are looking for a Chinese restaurant, these are one of three of thousands of different ways in which you can query your smartphone and you will more or less get the same answer. So this demonstrates that a computer can now understand human language. Many of our favorite email clients, like suppose if you are using Gmail, I use Thunderbird, can automatically sort out spam emails from non-spam ones. So in this slide here, you see two emails. Both of them are offering me money. So how many of you think that the red boxed email is a spam email? How many of you think it's spam? Can you raise your hands if you think that the red boxed email is spam? Okay, only a few of you. But my computer is able to correctly identify this as a spam email, even though it's offering me a lot more money than this blue boxed email, which is offering me just a modest $2,300, but it's a non-spam email, it's real money. Okay? And this was done automatically by my Thunderbird email client. A computer can now translate better than most humans. So here is an example of an English sentence being translated to Hindi, and this is just a pair of languages. Now tens of thousands of language pairs spanning over the entire world can be automatically translated. Now you can converse with a computer and you can engage in two-way dialogue or use a recommendation from a computer to assist a conversation that you might be having with other humans, and very often your machine is able to mimic a human. Forget about correct English. Now a machine can even substitute your grammar teacher, so you can feed to it an incorrect English sentence like she, Tom is catched by policemen in park at last night. This is not a made up sentence. This is from excerpt from a sentence from essays written by students in Asia, and a computer can correct the grammar errors in this sentence. So all these evidences seem to demonstrate that computers can now read and understand natural language like English, and my examples just happen to be English, but it happens you can have similar applications across several other languages. And that is somewhat unsettling maybe from an anthropological viewpoint, because for a long time we thought that the capacity to acquire and use language is a key aspect that distinguishes humans from other beings. And now we have machines which are able to speak and understand language, perhaps in ways and at scale which far surpasses human capacity. So how do machines acquire language, and how is their method of language acquisition different from the way a human child acquires language? Okay? So first let us look at the way a child acquires language. So there is some reason to believe that a child is born with the ability to produce 40 sounds, and it takes them roughly 10 years to, excuse me, there is some echo or some sound on the background. Okay, I am going to ignore that. So a child is born with the capacity to utter 40 sounds, and it takes them roughly 10 years to gain mature mastery over their native language. And they achieve that mastery through many different stages of curriculum learning. So initially a child learns nouns through conversations, thousands of hours of conversations with parents and relatives, where they learn to identify physical objects with nouns, then they understand words, then they go to maybe simple two-word sentences, and so on and so forth. In parallel, they learn to read, again in stages. First they understand alphabets, then they go to words, then to two-word sentences, then they go through different levels of readings of higher and higher complexity. And at the end of it, they understand when they hear a word what that means. I do not know, I am not a neuroscientist, but we humans have a way of representing the meanings of words in our brain. But we can certainly see that when you present to a human a word, they can immediately associate with lots of other words which are related to that current word. Now we will see how machines do the same kind of association. Actually, machines cheat. Machines cut short this painful curricular learning stages, and they are able to get more than 10 years of learning within a few days, because they have immense capacity to process information at a dizzying pace. So the whole of Wikipedia can be processed in just 30 minutes by a modern compute server. So if you think of all the books of the world which have been digitized, a computer can go through, kind of speedily read each and every word in that book. And then at the end of it, without any intervention from humans, from parents, from relatives, they are able to understand the meanings of words. Now, in the case of computers, we know how they represent words and their meanings. So in modern AI systems, the meaning of a word is represented as a vector in some high dimensional space, say typically 100 or 300 dimensional space. And that vector is called the embedding of a word, or a word embedding. And now in this slide, I am showing the word embeddings of this 100 dimensional space projected onto a 2-dimensional space. And you see that there are words which are related to kitchen appliances, words related to bathroom, and words related to hardware tools. They have all been conveniently clustered together so that related words appear close together in this geometric space. So how does a computer come up with these word embeddings? So you take discrete words, you take tomes and tomes of books, and you get these numbers, you associate each word with a 100-dimensional real vector, and how is that done? Without any intervention, without any explicit dictionary of what each word means. So that is done using a very clever trick. You all might have heard that a man is known by the company he keeps, and the same applies for words. The meaning of a word can be derived from the company it keeps, so that similar words appear in similar sentences. So suppose if you were trying to identify that fan and light are somehow similar, you would most likely, while you are going through all the online books of the world, will encounter sentences where fan and light appear in similar company, not exactly the same company, but similar company. Okay. And if you think algorithmically, this is done using a famous algorithm. It's called the word-to-vec algorithm. So in this algorithm, the algorithm goes through all books sentence by sentence, and the moment it picks up a sentence, it finds the center or the middle word of the sentence and tries to come up with an embedding of the word so that it can predict the words to its left and right. So here you see an example sentence. A snippet of a sentence which contains words like problems turning into banking crisis as so on and so forth. And now we are going to come up with a 100-dimensional representation for the word banking such that this 100-dimensional vector will be close to the 100-dimensional vector of words to its immediate left and to its immediate right. Okay. Now, if I present this in the context of just a single sentence, it might look a bit surprising, but if you repeat this process over billions of sentences, suddenly the embeddings start making sense, and that's what we saw over here. So these embeddings that you see in these slides were obtained by running the word-to-vec algorithm over, if maybe billions, not maybe millions of sentences. Okay. So you read each sentence, and in each sentence you try to get the middle word to be close to the words in its surrounding, and when I say close, it's close in this 100-dimensional space. Okay. And at the end of it, we magically are able to put semantically related words in close by in this 100-dimensional space. So that was about words. Now let's go to sentences. We all know that it's not just enough to understand isolated words, and an essential part of a language is how the words are stitched together to form a sentence. And we know that the order of words matter. So Ram hit Shyam is not the same as Shyam hit Ram. And now for AI systems, another important requirement is that we want to represent sentences of variable lengths in again as a fixed dimensional vector, so that we can do further processing on this fixed sized objects conveniently. So like the way we came up with embeddings of words, we would also like to come up with embeddings of sentences. Now, how do you convert sentences, varied sentences of any number of words from 2 to 20 words into a fixed dimensional vector? And of course, for sentences, we would like the vector length to be larger. Maybe we want 1,000-dimensional vectors to represent sentences. So how do we do that? So in the deep learning / machine learning literature, there is a structure which is designed for this summarization task, which are called recurrent neural networks. The term recurrent should give you a bit of clue about how these networks work. So, essentially in these networks you consume the input, in our case the input are words. So, you consume each token in an input sentence one at a time, and while you consume a sentence word at a time, you maintain a state, and we are going to generically use the letter H to denote the state. And with every new input, every new token, you update the state using a function which has parameters. So, the parameters in this particular diagram here are W, U and B, and we are going to use examples to learn these parameters. So, suppose we are now going to use these RNNs on sentences to get a summary or an embedding of a sentence. So, let us say you have a sentence which starts as follows: the students opened their exams. So, an RNN will be used to collapse this sentence into a fixed dimensional vector as follows. We will start with some initial state, and then we will read the first word. Of course, the word will now be represented as its embedding. So, we will read the embedding of the first word and we will get a new state, and then from that from this state which is H1 here, we will compute the second state by after reading the second word, in this case it is students. So, we read the embedding of students and compute the second state, and so on and so forth, and after you have consumed all the words, the last state can be called the embedding of the sentence. And once you have a fixed dimensional embedding of the sentence, you can already solve some tasks. So, the easiest tasks in the set of examples I gave you was the task of telling whether an email is spam or not. We call this a classification task. So, you are given as input an email and you have to assign a class label, which it could be either spam or not spam. And now this task becomes very simple once you have converted sentences, and now in our case a sentence is an email, into a fixed dimensional vector. So, again if you think of this 100 dimensional vectors of representing sentences being somehow projected onto the 2-dimensional space, which is the only space that I can show to you right now, then we would like to learn the parameters of that sentence summarizer or the RNN, such that the spam emails, let us call these the red dots, are clustered together and separated away from the non-spam emails, which are these blue dots. And once you have these embeddings which achieve such clusterness, it is easy now for a machine to learn this separator boundary, and when a new email comes, you can check in which side of this separator that email lies, and then you can classify that email as spam or not spam. Okay. So, at the end of this, now we have been able to understand, at least at a very coarse level, how one of the simplest tasks demonstrating a machine's capability of understanding language is actually solved within a machine. And if you see that the machine has taken a lot of shortcuts, there has not been any sort of systematic deep understanding of the language. We have somehow used lots of data to kind of solve the end task of email classification without really understanding the content in the way in which humans understand content. Okay. And we will see this pattern being repeated throughout. So, in order to solve now the more complex tasks of say translation or holding conversations, we need to next understand how humans can write. How can they compose a sentence? So far we have all seen only how machines can take a sentence and understand the import of that sentence, and now we will see how a machine can generate a sentence of its own. Again, the way in which modern machines generate sentences is very far from how humans are taught to write sentences. In particular, for the school students in the crowd, one good news is that machines are not taught grammar explicitly. They don't have to understand subject, object, verbs, adverbs, adjectives. And there is no stage-wise learning that they are subjected to. So, in fact, they just train a model which can predict the next word in a sentence given the prefix of the sentence or the set of previous words in the sentence. So, every sentence has a special marker which is the start of sentence symbol, and then when it is fed the start of symbol marker, it has to generate the first word of the sentence. The first word of the sentence is then fed as input, and then the machine is asked to generate the second word, and so on and so forth until the machine generates another special token which marks the end of the sentence. Okay. So, that is how a sentence is created. So, let us understand a bit with respect to how that is done in terms of neural circuitry. So, we are going to learn to output the next word, and here again we are going to use a recurrent neural network. So, earlier you saw that a recurrent neural network was sort of clipped at this point, where it was taking as input words and it was producing a summary, which is what we thought of as the sentence embedding. Now, we are going to use each state of this RNN to generate the next word. So, I am going to after seeing the word the, I would like to generate the next word, which is students. After seeing students, I would like to generate the next word, which is opened. I am sorry that these words have been shifted here on the head, but you get the idea, and so on and so forth. And again, the machine learns the parameters of these RNNs. So, here in these RNNs, you have parameters like W, U, and WE, which are learned by going through again the billions of text sentences in online books and in Wikipedia kind of resources. And again, when you do such learning over huge amounts of data, then even a machine can start generating natural looking sentences. Once we have the capability to read sentences and write sentences, we can become ambitious and try to solve tasks like translation. Actually, translation is not a new problem. Computer scientists have been wanting to solve the translation task for over 50 years. And around the time that I started my PhD, say in mid 1990s, most of translation was done using a methodology which was called statistical machine translation. So, in that methodology, you were required to create huge dictionaries, and these dictionaries were not at the level of words, but phrases, which is bigrams and trigrams of words. So, here is a snippet of maybe a candidate translation dictionary, which says for some bigrams or trigrams what the corresponding translation could be in English. So, you had such dictionaries as one of the major inputs to the statistical machine translation system, and then you had elaborate grammar rules. Okay, these were often painstakingly developed by linguists. And then you had a bit of learning which was done using a limited amount of labeled data. And then for some commonly occurring language pairs for which there was lots of examples of correct translations, the machines could do a somewhat okayish translation, but those translations were clearly machine generated, and they only served very crude purposes. Now, that changed when AI technology advanced, and now we no longer depend on simple statistical methods, but we have the power of deep neural networks. And one technology in particular which has contributed to remarkable advancement in the translation technology is what is called sequence to sequence learning. So, in sequence to sequence learning, you train a model which can take as input a sequence of tokens. In our case, this sequence of tokens are sequence of words, which is a sentence in one language, and you learn a model through lots of examples to generate an output which we are going to denote as y, and y consists of another sequence of tokens, and hence the name sequence to sequence learning. Now, sequence to sequence learning in state of the art deep learning systems for translation is handled through what are called encoder decoder models. So, in an encoder decoder model, you first encode the input x into fixed dimensional real vectors, and we already saw how that can be done, and we were calling them sentence embeddings. But now for translation, we are going to take the sentence embeddings as input to the next stage, which is called the decoder, which is going to generate the y or compose the sentence one token at a time. We have already seen how sentences are composed. It's just that now we are going to compose sentences conditioned on an input sentence in another language. So, we are going to do conditional sentence generation. And if for some of you who are comfortable with statistics, essentially we are trying to create a probability distribution over the space of output sentences given an input sentence by learning parameters which we denote generically as theta, and this distribution is obtained by just saying that I am going to generate this y which consists of t tokens in turn by going over generating them token by token starting from y1 to yt minus 1, and once I have generated the first t minus 1 sequence tokens, I can generate the tth token through some neural circuitry which we are going to go over next. So, here is a very popular diagram which is used to explain how translation is done in modern deep networks. So, it looks a bit complicated, but I am going to take you through this diagram step by step. So, in the input here at the bottommost sentence here, you see is an English sentence. It says economic growth has slowed down in recent years. So, that is our input x, and we are going to first convert each of these words into their embeddings. So, what you see is this is what is called the embedding layer. It converts words into their 100 dimensional embedding. And now we are going to use a recurrent neural network to summarize this input sentence into a fixed vector, which is what I am denoting by this red circle over here. This is a recurrent neural network which has taken the words one by one and created a summary, and now we are ready to generate the target sentence or a sentence in, let us say, our target language Hindi by using another recurrent neural network, and this is the neural network which can compose sentences or generate sentences. It's just that this network is going to start with their initial state as the sentence embedding of the English sentence. So, we start with that, and then we generate a distribution of the possible first words of the sentence. After we have generated the first word, we feed that as input and generate a distribution over the second word, so on and so forth. Okay. So, this is very crudely how translation is done in modern deep networks. But this was just a kind of a simplified diagram. In practice, a translation system has billions of parameters, and we do not just use one recurrent neural network. We might use like some 8 to 16 layers of neural network. So, this diagram here is showing the architecture of one high performing machine translation system which is based on deep network. It is called GNMT model. This is as of 2017 and things have evolved a lot since then. But even if you look at this 2017 diagram, you will get a sense of the complexity that is involved in creating modern translation systems. So, we have this encoder layer which consists of 8 levels of RNNs. And I did not have time to go through it. You do not just look at the input as a fixed dimensional vector. Sometimes you might want to look at specific focused words of the input, and that is done through attention. And then this is the decoder. Decoder is another stack of 8 recurrent neural networks, and that is what gives us the words one by one. And there are lots of details and engineering that have to be done right in order to get good accuracy on even easy translation tasks like say going from English to French, which is lot more related than say going from English to Hindi. So, here are again some results. These are also as of 2017. What you see is for 6 different language pairs, you see these numbers which you can think of as quality scores, higher is better, from 3 sources. One is where you use this conventional statistical machine translation systems to generate the translation. Second is when you use modern deep neural networks to do the translation, and third is when you use humans to do the translation. And you can see, of course, at least as of 2017, humans provided the highest scores, but the deep learning based model is quite close. Okay, compared to the conventional statistical machine learning systems, which says that we have come a long way. Okay. So, that was translation. Now, how does a machine learn to converse? Actually, surprisingly, the basic technology is still the same. We are going to use a sequence to sequence learning model which will be trained on huge number of conversations. So, most large companies have access to conversation records of the billions of people around the world which use their software. So, suppose many of us academics use Hangouts a lot, and companies like Google record conversations that we conduct on Hangouts. If you are looking for public sources of conversation data, you can hit websites like Reddit. And so, this way you have lots of conversation snippets over billions of users, and you can train a sequence to sequence model to generate the next sentence in a conversation given the context of the previous sentences that has been spoken by the other party. So, again it is just like a you can use a sequence to sequence learning model to learn a conversation model. And the same thing can be applied even for grammar error correction. So, you can feed as input an incorrect sentence, and you can ask to generate a correct sentence, and again you will be training the machine to generate the correct sentence by using several examples. Okay. So, but now I am going to talk about a shortcut that we took to train tasks for grammar error correction, which is much more efficient than what was done by existing neural methods of grammar error correction. So, the existing methods, as I just said, they follow the encoder decoder approach where you feed the incorrect sentence and you get a summary of that incorrect sentence and you generate the output sentence token by token. Now, this recently just last year we developed a system which was based on this founding idea that for grammar error correction it does not make sense to generate the entire output from scratch. In fact, what we need to do is just generate local edits, and that is best handled by not posing grammar error correction as a sequence to sequence learning task, but as a much simpler sequence labeling task. In a sequence labeling task, your goal is to label each token or word of a sentence. Okay. So, we are going to take each token of this sentence and we are going to label that word with the edit command, which when applied on that word will generate the correct sentence. So if I take this sentence, now for the first word I do not need to do any edit. So the label I will be assigning to the first word is copy. To the second word again I will be assigning a label of copy, so on and so forth. But then when I see the word this is incorrect. So to this sentence I am going to assign the label delete, and to the word after that I am going to assign the label replace, because I am going to convert this cached to caught. So this is a replace command. And we have another command which is append. So here the article the was missing. So I am going to create a command which adds a the after the word in, and so on and so forth. So by converting the grammar error correction into a sequence labeling task, we are able to create more efficient networks, and then we can learn with smaller amount of data. So I showed you that complicated model which was used for sequence to sequence learning for a translation task, whereas for the sequence labeling task we just have one neural network layer which takes our input sentence and generates an embedding of the word in the context of the sentence, and using that we just predict the command or the edit that can be applied on each of these words to generate the correct sentence. So we just leave at this. So we generate these edit commands, and now you can just apply these edits on the sentence and get the correct sentence. And using this much simpler model, we are able to get comparable accuracy than the more expensive sequence to sequence models. And more importantly, we are able to do grammar error correction at 5 to 15 times faster speed than the more expensive sequence to sequence learning models. And now even for grammar error correction, humans have achieved, the machines have achieved accuracies which rival human accuracy for grammar error correction. So that's it. Now we are, I have reached the end of my talk. So essentially I just want to conclude by first summarizing the key points that I wanted to convey in the talk, and then I will end with some thoughts on what is lacking. Okay. So first we went through the notion of word embeddings. We saw how a computer can just go through unlabeled text, just the raw text as it exists, and automatically infer the meaning of words, and those meanings are represented as word embeddings which are just 100-dimensional vectors. Then we saw how computers can understand the meaning of sentences and how they are able to generate sentences again by going over available text as is and learning from them a probability distribution over the next word in a sentence given the previous words. And once we had these two tools ready, we were able to solve the translation tasks using the encoder decoder models, and we are seeing that model translation systems are able to achieve accuracies which have not quite reached human level accuracy, but they are quite close. And then the same technology applies for conversation, and for some other tasks like grammar error correction, you could solve it using sequence to sequence learning, but this is some work we have shown in our lab that you are much better off casting it as a sequence labeling task. And through all these different tasks, we have demonstrated that machines can read and understand human language pretty well. Okay? And in some cases, they are even surpassing human accuracy. But that was an overly optimistic picture. Now, for some of us who are behind the scenes, we see plenty of embarrassing cases of failures which demonstrate that by shortcutting the learning process, by converting everything into income sentence, and here is a black box and I am going to produce an output which matches the specification as obtained from huge amounts of labeled data, they are able to kind of parrot what is being told to them, but they are not able to generalize, and that reflects in terms of major brittleness in the predictions that they make. So in our own grammar error correction system, system, we found that if I feed a sentence like I arrived at Mexico City 1 month ago, I get the correction that I arrived in Mexico City, but when I convert Mexico to Azerbaijan, I do not get this correction. Whereas for humans, this is unthinkable. If I know that at should be replaced by in when you are talking about visiting a city, it should apply for all cities. But our system does not do that. And this is just our grammar error correction. If you look at the research literature, there are now many such cases of dissection where people have shown translation systems, question answering systems to be equivalently brittle. And now one hot area of research in the deep learning / NLP community is how to make these models more robust and more human-like. Okay. Second, a big problem of modern systems is their heavy reliance on huge amounts of label data. For many Indian languages, we do not have such nicely labeled paired sentences. How can we do learning? How can we learn models which do automatic translation in such cases when we have only limited amount of label data? And third, humans don't just understand language in terms of words, their meanings and and grammar, but rather our language is tied to common sense, to knowledge, to facts, to information. So, how can we bring in computers knowledge, at least for some factual knowledge, is represented by structures called ontologies like knowledge graphs. So, one other area of research in the NLP community is to tie such language tasks like conversation, translation to facts and knowledge which are represented in knowledge graphs, or to tie them to common sense which might be represented in some other systems like psych. Okay. So, the field is open for youngsters like you to investigate more. We are not yet done in spite of what I might have said in the first 90% of the talk. There are lots and lots of corner cases and embarrassing situations where modern black box AI machines for language understanding fail, and we have a long way to go. With that, I would like to conclude. Thanks.